Hello everyone. Today we are going to talk about finding a Fourier series expansion for a function and an interval alpha less than x less than alpha plus 2 pi. That means we are going to expand functions into Fourier series expansions uh, when function is periodic with a period of 2 pi. Okay. So by this Fourier series is an infinite series and uh, particularly expanding function into infinite sum of sines and cosines, the trigonometric functions. So let us take the definition of Fourier series expansion of functions, particularly when the function is periodic with period of 2 pi. So the Fourier series for the function fx in the interval uh, when x varies from alpha to alpha plus 2 pi is given by this series where alpha um, can take a number such that uh, alpha is any number and the period of this function is 2 pi, and then the function can be expanded into infinite series where infinite series is of cosine terms and sine terms. Okay, so this constant is due to this summation. Basically, if I write it as n0 to infinity, then this term will come here. Okay, so for n is equal to 0, a naught term goes outside, and then instead of a naught we are writing this constant as a naught by 2 for a specific purpose. I will let you know in a while. And for n is equal to 0, this sine 0 is 0, so that term is not present, and so we are writing this infinite series as a naught by 2 plus uh, sum of infinite terms of cosine and sum of infinite terms of sine, and here these a naught, an, bn, they are Fourier coefficients, or they are unknown constants to be evaluated so that we can know what exactly is this infinite series. Okay, so our one job is to find a infinite series of fx, that means an expansion of this form, and to do that we will evaluate these a naught, an and bn, and then that sum, or that series, its sum will be equal to this fx if this right hand side is convergent. Okay, so I'm writing it equal to fx, but you have to be careful that this function's infinite series, this right hand side, uh, if it is convergent, then converges to this fx or not. Okay, so uh, about these constants, how to evaluate them, then these coefficients we can evaluate uh, by using the Euler formulas. Okay, and the Euler formulas are that a naught is given by 1 by pi alpha to alpha plus 2 pi integral of fx dx. Okay, this function. Similarly, an can be calculated as 1 by pi integral alpha to alpha plus 2 pi of fx cos nx dx. Okay, and similarly bn can be calculated as 1 by pi integral alpha plus 2 pi fx sin nx dx. Okay, so you have to remember that for a function which is periodic with a period of 2 pi, we can write the function as infinite series this, where these constants can be evaluated using these three integrals. Okay, so then I said that we have written the constant a naught as specifically as a naught by 2, just for one reason, so that to make these formulas symmetric. If I simply use a naught here, then this formula will change here. Okay, so just to make the symmetry of 1 by pi, we use the constant a naught by 2. Okay, so let us first prove that these three formulas are true, and that these Euler formulas are actually calculated or can be seen to give the value here. Okay, so let us prove these three formulas first. Okay, so to prove this, let fx as a infinite series expansion of this form, that fx we can write as the infinite series of this form, and then we'll prove that these three formulas are true for the constants. Okay, so to prove this, so I'm saying is that the Fourier series for the function fx in the interval alpha to alpha plus 2 pi is given by this infinite series. Okay, so let this function has this infinite series expansion. Okay, now to calculate the first coefficient a naught, we simply integrate on both sides of this equation with respect to x over this interval. Okay, so to find a naught, okay, integrate both sides with respect to x with alpha alpha plus 2 times pi. Okay, and then this is the integral of sum, and it will be same as sum of integrals. Okay, because the n's are constants, and so it can be written as sum of integral of cos of nx, and we know integration of cos of nx over this period, if you calculate it, is 0. Similarly, integral of sine nx from alpha alpha plus 2 pi, you can calculate it, is 0. Okay, so these two summations will be 0, and the integral here is integration of 1 dx, so integration will be x, and then you can put substitute the upper limit minus lower limit, so what we will get is 2 pi, so 2 will cancel out and I will have pi a naught from here. Okay, so this in left hand side equals this first integral will give integration x with limit, and then we substitute limit to find it as pi a naught. The rest of the two integrals are exactly 0. Okay, so now we can calculate a naught as 1 by pi of this integral. Okay, so this is one first result. To find the this coefficient an, we multiply both sides of this equation with the cos of nx. Okay, for some fixed n. Okay, and then we integrate over this interval alpha alpha plus 2 times pi. Okay, so for an we multiply both side with cos of nx and integrate. Okay, so left hand side is this function times cos nx dx integral equals to a naught by 2 integral of cos nx, cos nx into 1, and plus then integral cos nx into summation of this. Okay, and plus integral cos nx into this summation. Okay, now again on the right hand side, this first term integral of cos nx over this limit, if you solve you will find that its integrals value is sine nx by n, and if you substitute limit you will find that the value is 0. And then for here we know result. Okay, so integral of sum, we take this becomes the integral of cos nx into sin x nx, and then we know that integral of sine of mx cos nx dx is all 0 over this limit, so this third term is 0. And in the second we know this n which is here in the integral, it is a fixed n, but here this n is varying, n is 1 to infinity. Okay, so it is like cos nx into cos 1x, cos nx into cos 2x, cos nx into cos 3x, and so on. So we know the integral for this limit of cos nx into cos mx dx is 0 when n is not equal to m. So this will be 0 for all n except when this n takes value n here. That means for cos square nx this will give value, for all other it will be 0. Okay, so this summation infinite sum will actually give only one integral value when cos nx is multiplied with cos nx. All other, for all other n it will be 0. So this first is 0, third is 0, and it will give only one function. Okay, so basically the right hand side will become an integral of cos square nx dx, and cos square nx we can expand as 1 plus cos 2 nx by 2, and then by linearity it is integral of first 1 by 2 plus integral of cos, and integral of cos is 0, so only 1 by 2 integral will give us the half of x, and then we substitute the limit to find that it is an pi. Okay, so immediately we can calculate an as 1 by pi of this. Okay, so that's our second result. Similarly, to find the third result, we multiply both sides of the equation with the sine nx function. Okay, and integrate over the limits. Okay, So multiply both sides with sine nx and integrate over this limit. Now in this case the first integral on right hand side is 0, the second is 0, and the third will give value only when it is sine nx into sine nx. For integral sine nx into sine mx dx when n is not equal to m over these limits is 0. Okay, so again right hand side will be bn integral alpha to alpha plus 2 pi sine square nx dx, and this can be written as 1 minus cos 2 nx by 2. Again similarly cosine integral will be 0 and it will give x by 2, and then you substitute limit x value upper minus lower, so it will be 2 pi. Okay, so half of 2 pi, so it simply gives pi. Okay, so then we can calculate bn, so bn is this third result. Okay, so this is very simple proof of Euler's formula for the Fourier series expansion of the function. Okay, now I take say example that how to find the Fourier series expansion for the function say fx is equal to x in the interval 0 to 2 pi. Okay, so given this function fx is equal to x in the interval 0 to, oh here it is 2 pi not pi, 2 pi. Okay, and uh, we can expand the function as a Fourier series expansion in this interval 0 to 2 pi because the period is 2 pi, and we know the expansion that fx is equal to a naught by 2 plus summation a n cos nx plus summation b n sin nx, and if you compare these two then you will see that alpha is 0 here. Okay, and then we just need to find out these three these constants a naught, all the ans and all the bns. Okay, so infinite constants are there, but Euler formula allow us to calculate them easily. So the first constant a naught is simply 1 by pi integral uh, over the interval which is 0 to 2 pi here of fx dx, and fx is x. Okay, so it is 1 by pi 0 to 2 pi integral of x dx, x integration is x square by 2, substitute upper limit minus lower limit, so immediately we have the value of a naught as 2 pi here. Okay, for an we know it is integral 1 by pi integration 0 to 2 pi of fx cos nx dx, and fx is x. Okay, so x time cos nx, and so it's a product of two terms, so we use integration by parts. Okay, first function x, second function cos nx. So first function integration of second, so integration of cos nx is sin nx by n minus derivative of first which is 1 and integral of this, so integral of sin nx by n is minus cos nx by n square, so minus minus becomes plus here. Okay, so double integral of this will give one negative sign and 1 minus sign for the rule of integration by part, so it becomes a plus sign here, and then we substitute the upper limit minus lower limit. So when we substitute 2 pi, so sine of 2n pi is 0. Okay, and we put lower limit 0 here since sine 0 is, so this first term is 0 for both limits, and uh, upper limit cos 2n pi is 1 minus cos 0 is also 1, so 1 minus 1, so this term is also 0. Okay, so a n terms are 0 here. Then we calculate the bn's. So bn is 1 by pi integral x sin nx because x is fx, and then we have to multiply with sin nx. So bn is 1 by pi integral 0 to 2 pi x sin nx dx, and then we have to again integrate by parts. First function as x, integral of second function which is minus cos nx by n, then minus derivative of first, so x derivative 1, and integral of this which is minus sin nx by n, and so minus minus again become plus, so we have sin nx by n square. Substitute the upper limit minus lower limit, so sine function becomes is 0 for both limits, so second term is 0, and at the lower limit x is 0, so this term is 0, only at the upper limit it will give value as minus 2 pi by n and cos of 2n pi which is 1, so it will give value uh, minus of 2 pi by n, and there is a 1 by pi outside, so we get 1 by n pi minus 2 pi, which is minus 2 by n. Okay, so once we have a naught, a n and b n, we can substitute these three back here to write the Fourier series for the x. Okay, so the Fourier series expansion of fx, which is x, is equal to a naught by 2. Okay, so a naught is this, so a naught by 2 is simply pi minus summation n is equal to 1 to infinity a n cosine x. A n is 0, so this complete summation is 0, and plus summation b n sin n x. So b n is minus 2 by n, so minus 2 by n sin n x. So this right hand side is the Fourier series expansion of this function x. Okay, in the interval 0 to 2 pi. Now just to check whether this, if we calculate this infinite sum, okay, put n is equal to 1 2 3 and check this infinite sum whether it is equal to x for all x in this. Okay, so I'm just giving you this, visualizing this, that if fx is in this and if we write it as an infinite series, okay, and so if we expand this into infinite series, then for n is equal to 1 2 3, what happens when n is 1? That means this will give only one term, so only pi minus 2 sin x. When n is 2, okay, so it takes some two values from this sum, then that means pi minus 2 sin x minus sin 2x, and so on. So what happens? Okay, so if we take n 1 2 3 4 so on, what exactly happens? You can see that for n is equal to 1 and 2 3 4, as the number of terms, we take large number of terms, this right hand side actually becomes this straight line, fx is equal to x. Okay, so I plot it for some n is equal to 101. You can see that this sum is actually converging to this line. Okay, so this is one example. Let's take one more example. Say expand the Fourier series for the function fx is equal to x plus x square in the interval minus pi less than x less than pi. Okay, so the plot is given here. This fx is x plus x square in minus pi to pi, and so the function is again periodic with a period of 2 pi. Okay, with the alpha value minus pi and alpha plus 2 pi value is pi. Okay, so if alpha is minus pi, it is automatically satisfied. So again the we let the Fourier series for this function is given by this a naught by 2 plus summation a n cosine x plus summation b n sin n x, because the period is 2 pi, and you can compare and see alpha is minus pi, which satisfies this. Okay, and then we have to calculate the constants, a naught, all a n's, all b n's. Okay, so to find a naught, it is simply 1 by pi integral of this fx. Okay, so 1 by pi integral of fx dx, where now limit is minus pi to pi because the interval is this minus pi to pi. Okay, so we simply integrate this. Okay, so x integral is x square by 2, x square integration is x cube by 3. Substitute the upper limit minus lower limit, and you see that its value, a naught value, is 2 pi square by 3. Okay, similarly we can calculate an. An is 1 by pi integral fx cos nx dx. Okay, and now again we have to integrate by parts. X plus x square is taken as first function and cos nx as second function. So first function integral of second function minus derivative of first and integral of second, and then plus the derivative of this first and the integral of second. Okay, so I've done integration by parts in one step. Okay, hope you know if one of the polynomials, then we can do this. Okay, and then you substitute the upper limit minus lower limit. Okay, so sine n pi is 0, so and sine of minus n pi is also 0, so sine functions are 0 for both limit, and cos n pi, we know its value is minus 1 raised to power n. Okay, so we can substitute it here and find the an value. Okay, this first term will be 0 for both limit, third term will be 0 for both limit, and this second term will give for pi and minus pi, and then we can solve that. Okay, and use the formula that cos of n pi is minus 1 raised to power n, and for minus pi it is cos of minus n pi, and cos of minus theta is cos theta, so it is again minus 1 power n. Okay, so you can combine those two results to find this value. Okay. Similarly, we can find bn as 1 by pi integral minus pi to pi fx times sine nx dx, and then again use integration by parts. Okay, twice. So first function, okay, x plus x square, integration of sine minus cos nx by n, then derivative of this x plus x square with minus sine, so 1 plus 2x, integral of this with minus sine nx by n square, then sign changes to plus, derivative of 1 plus 2x which is 2, and integral of minus sine nx by n square which is cos nx by n cube. Okay, and then there is no further term because this derivative becomes linear, then constant, next derivative will be 0, so all terms are 0 further. Okay, so again substitute the upper limit minus lower limit, the second term will be 0 now for both the limits because there is a sine function, and then we substitute upper limit in first and third term and minus lower limit in first and term, and then you can combine the terms to find that this is the result. Okay, use the fact that cosine pi is minus 1 raised to power n. So once we have a naught an and bn, you can substitute them back here to write the Fourier series expansion. Okay, so a naught a and bn back here in this series. Okay, so once we substitute it here, okay, so you'll have the infinite series. If you put n is equal to 1, 2, so on, you can write the expansion in this form, and then for different values of n, you can see that the graph actually converging to this curve x plus x square in minus pi to pi. Okay, so this is how we calculate the Fourier series expansion. Now the one question is that whether this is always true, that we can find the Fourier series expansion of all functions or not. Okay, so are there functions for which Fourier series expansion is not possible in a certain interval, or we can find Fourier series expansion of any function. Okay, so this question is answered through these conditions, which are known as Dirichlet conditions, and they are the sufficient conditions for the Fourier series expansion of function. And these conditions says that the function fx has to be periodic, single valued and finite. Okay, so function is, if it is given in one period, then you can assume that the say it is periodic, and so outside that period it is repeating. It has to be a single valued function. Okay, and it has to be finite, so a function should not go to plus infinity or minus infinity. Okay, in that interval. Then the function fx has finite number of discontinuities in any one period. So we just calculated Fourier series for like fx is equal to x, uh, and fx is equal to x plus x square. Those were continuous functions, but here it says that we can also find Fourier series for discontinuous functions with finite number of discontinuities only. Okay, so these discontinuities will be jump discontinuities. Okay, because the function has to be finite. Okay, so at discontinuous point of discontinuity, function should not be infinite. Okay, and then there is the third condition, that the function has a finite number of maxima and minima in any one period. Okay, so in that period the maxima and minima should be finite in number. Okay. So if a function satisfies these conditions, then these conditions are sufficient to know that the Fourier series expansion for the function is possible. Okay, uh, so when the conditions are satisfied, the Fourier series converges to fx at every point of continuity. That means we can expand the function into infinite series of sine and cos, and that series, the right hand side series, actually converges to the function at every point of continuity. And because there can be a jump discontinuity, so at the point of discontinuity, say at x is equal to c, there is a discontinuity, then the sum of the series is equal to the mean of the limits of the right and left at that point. That means the function well some value is actually equal to this, which is the uh, average. Okay, because when epsilon goes to 0, f of c minus epsilon means the value of function from left, and is the value of function from right. Okay, there's sum divided by 2, so the average value at the point of jump discontinuity. So if You expand a function into infinite series of sine and cos, that means into Fourier series, and if function satisfies all these conditions, then that means the right hand side infinite expansion will actually converge back to the function at each point of continuity, and at the point of discontinuity it will give this value. Okay, so this is important. Okay, so it's possible to find the Fourier series for if the function is has a jump discontinuity. Okay, so let us take one example of that. Okay, say expand in Fourier series the function fx is equal to -1 in minus pi to 0 and 1 in 0 to pi. Okay, so function is -1 in minus pi to 0, and then there's a jump of 2 units, and the value of function becomes 1 from 0 to pi. Okay, so function is periodic. Okay, so on the left of this and on the right of this the same curve follows. Okay, the function is single valued. For every x there is only one value of fx. Okay, the function is finite. Okay, at every point on this one period the function has a finite number of jump discontinuities. Okay, so there is only one jump, and the function has finite number of minimas and maxima. So there is only one minima here. Okay, there are infinite points of minima, but the minimum value is only one. Okay, and there are infinite points of maxima, but there is only one maxima. Okay, maximum value is only one. Okay, so we can expand and find the Fourier series expansion of this function. Okay, so as we said, this function is again a periodic with the period of 2 pi. Okay, so minus pi to pi, so 2 pi is the total period. So we can assume that the Fourier series expansion of function is this a naught by 2 plus summation a n cos n x plus summation b n sin n x. Okay, and then again we have to find a naught, a n and b n. Okay, so formulas are known. A naught is 1 by pi integral minus pi to pi of fx dx, but now the function fx is a piecewise function, so we can divide this integral into two parts, minus pi to 0 and 0 to pi. In minus pi to 0 function value is -1, and in 0 to pi the function value is 1. Okay, so this integral is sum of two integrals, and each piece the function value is known. Okay, then we can integrate this. Okay, and substitute the upper limit and lower limits. So a naught value in this case is 0. Okay, then the ans we can calculate as 1 by pi integral minus pi to pi fx cos nx ds. Again fx, to substitute fx we have to divide this integral into minus pi to 0 and 0 to pi, and then substitute fx value -1 for first and fx value 1 for the 0 to pi integral. Then integration of cos nx is sin nx by n. Okay, and then we can substitute upper limit minus lower limit in this. Okay, so again because the sine function is 0 for these limits, the integral these ans are 0. Okay, and similarly we can calculate bns. Okay, so uh, 1 by pi integral minus pi to pi fx sin nx. Okay, and then we have to divide that for 0 to pi and minus pi to 0, and in minus pi to 0 the function value is -1. So this first part is function value -1 minus pi to 0, and function value is +1 in 0 to pi. Okay, so I have written this step directly here, and then we can integrate sin nx integral is minus cos nx by n, substitute upper limit minus lower limit, and then you can see that the value of these bn's are 2 times 1 minus -1 raised to power n over pi n. Okay, remember cos of n pi is -1 power n. Okay, so then substitute a naught, a n and bn back here to find the infinite expansion in terms of Fourier, and so you can see that function can be written as, because a naught and a n are 0, so cosine terms are not present, only sine terms are present, and if you expand, put n value 1 2 3 so on, we can write infinite series of sine terms. Okay, and then for different n values we plotted this to see whether for large n it actually converges to function itself or not. So you can see that when n is 1, 2, 3, this function shapes, and when n becomes large it actually becomes this step function. Okay, so it is actually converging back to this function fx, which is -1 in this interval and +1 in this interval. Okay, so this is about Fourier series expansion in the interval which is periodic with a period of 2 pi. Okay, in the next lecture we will generalize this concept of finding Fourier series in the general interval alpha to alpha plus 2c, where c is any constant. Okay, have a very good day.